Okay, so end of chapter problems for chapter 7 and 8. Let's bust this out. Let us do this thing. So, chapter 7, first problem is 26. Assume that an aqueous solution of a cation, represented as a blue sphere, is allowed to mix with a solution of an anion, represented as a red sphere, and that the following result is obtained. Which combination of cation and anion chosen from the following lists are compatible with the observed results? Okay, well, it's insoluble, so it cannot be sodium. Calcium chloride would be soluble, so it's not calcium chloride. Could be calcium carbonate. That would be a 1-to-1 ratio. Silver carbonates would not work. Oh wait, no, this is a 1-to-2 ratio. Yeah. So it couldn't be calcium carbonate. It would have to be silver carbonate. Silver carbonate would work. Oh, no, the red sphere, yeah, 2-to-1. So yeah, silver carbonate could work. Nickel carbonate could not. So it could be silver carbonate. Chromate, silver chromate could work. And let's see, I think that would be it. Yeah, so it would just be silver carbonate. This is all just based on solubility. We have an insoluble product, so that's what I'm working with. And it is a 1-to-2 with, or sorry, I should say 2-to-1. Two cations for every one anion. So that's what we're looking at. So silver carbonate and silver chromate seem to be the two possibilities. All right, who's next? 30, and then we're going to go straight through to 56. Every even number from 30 through 56. Okay. "30. Based on the positions in the periodic table, which of the following would you expect to occur? Red plus green goes to red plus green plus. No. Absolutely not. Because green is a halogen, and red is an alkaline earth metal. You're definitely not going to get, you're not going to oxidize an halogen. No, it's not going to happen. Blue and green plus goes to blue plus green. I could see that. That's silicon versus iodine. I could see iodine forcing silicon to oxidize. I can see that. Red plus blue plus goes to red plus blue. I could see that one as well. I could see both B and C in that one. So let's see. We're on page 267. I'll try and remember that. What do they say? Go slower, why don't you? Chapter 6. Come on. There we go, chapter 7. So, 30. And 30. No reaction would occur. Yeah, okay, good. My thinking is the same as theirs. So A30 is where we need to be for that. So 267. Going back. Okay, 32. Next page. All right, classify each of the following reactions as a precipitation, acid-base neutralization, or oxidation reduction. So in the first one, we have mercury 2 nitrate aqueous plus 2 sodium iodide aqueous makes 2 sodium nitrate aqueous plus silver 2 iodide solid. That's a precip reaction. 2 aqueous salts mix and you get an insoluble product, precip. HGO solid goes to liquid mercury and oxygen. That is very straightforwardly an oxidation reduction. The mercury is going from mercury 2 plus to mercury 0, so it's being reduced. The oxygen is going from 2 minus also to 0, so it's being oxidized. Finally, phosphoric acid plus potassium hydroxide. That's an acid-base neutralization. And now we write net ionic equations for each of the problems in 732. Okay. Rather quick and straightforward. I'm just going to go ahead and skip right to the chase for each of those. Cut to the chase. That's a Hollywood term. Okay. Hg 2 plus 2I minus goes to HgI2. Aqueous, solid. Next up, we don't have to worry. That already is the net ionic equation. And then the last one is just going to be H plus OH minus yields H2O. AQ, liquid. All right. 36. The following aqueous solutions were tested with a light bulb. Conductivity apparatus, as shown in Figure 7.1. What result, dark, dim, or bright, do you expect from each? Okay, they're asking, is this a strong electrolyte, weak electrolyte, or non-electrolyte? So potassium chloride, fully soluble, that is going to be a bright light. Methanol is an organic compound. It's not going to produce any ions in solution, so that is going to be no light at all, dark. And finally, acetic acid, that is a weak acid, so it's a weak electrolyte. You're going to get a dim light. 38. Individual solutions of barium hydroxide and sulfuric acid both conduct electricity, but the conductivity disappears when equal molar amounts of the solution are mixed. Explain. That's because barium sulfate is not going to be soluble in solution. And on top of that, the H plus and OH minus are going to react in order to produce H2O. So all of the ions disappear. Barium sulfate is insoluble, and you lose the hydrogen and OH minus. So this is, it is a combination of a precip reaction and an acid-base neutralization. All the ions disappear, therefore you have no electrolytes left. 740. Classify each of the following substances as either a strong, weak, or non-electrolyte. Hydrobromic acid is a strong acid, therefore it is a strong electrolyte. B, you have hydrofluoric acid. That is a weak acid, therefore a weak electrolyte. Sodium perchlorate, that is a fully soluble salt, so that is going to be a strong electrolyte. Ammonium carbonate, that's insoluble, so non-electrolyte. That apparently is where they're going with this. NH3, that is a weak base, a molecular base, a covalent base, so it is going to be a weak electrolyte. And finally, ethyl alcohol, or ethanol, is a non-electrolyte. 42. What is the total molar concentration of ions in each of the following solutions, assuming complete dissociation? What they're saying, it dissociates completely, therefore you're going to get more ions than just the individual thing. So potassium carbonate, you dissolve it in solution, K2CO3 solid is going to produce 2K plus CO3 2 minus when you dissolve it in water. So every unit of potassium carbonate is going to produce 3 ions. So the total concentration of ions is going to be more than just the concentration itself of the salt. So 0.750 molar, you're going to multiply that by 3. Let's see, 2.1, maybe 2.25 molar. Aluminum chloride, likewise, assuming complete dissociation, AlCl3, that would go solid. That is going to be Al3 plus 3 Cl minus. So it's going to produce 4 ions for every unit of the AlCl3. So you take this 0.355 molar and you multiply by 4 to get the total concentration of ions. 1.2, 1.42. All right, next up. Which of the following substances are likely to be soluble in water? Silver oxide is not. It's generally, silver is going to be, let's see, wait. That's a weird one, but silver oxide is not going to be soluble. Barium nitrate will be soluble, tin 2 carbonate will not, Fe2O3 will not. 46. Predict whether a precipitation reaction will occur when the following are mixed. Sodium hydroxide and perchloric acid. That's not a precip reaction, that's an acid-base neutralization. So technically, no precipitation. Iron 2 chloride plus potassium hydroxide, yes, you will get a precipitation. Hydroxides are typically insoluble unless they are mixed with, well, iron 2 is not one of the exceptions. Ammonium sulfate plus nickel 2 chloride. Nickel sulfate will not precipitate. It's not one of the exceptions. So this will not produce any precipitates. Sodium acetate, written backward for some reason, plus hydrochloric acid. Again, that will not produce a precipitate. All right, 748. Which of the following solutions will not form a precipitate when mixed with barium chloride? Lithium nitrate would not, potassium sulfate would, and silver nitrate would. So the only one that would not would be A, the lithium nitrate. The potassium sulfate would because you'd get barium sulfate coming out of solution, and the silver nitrate would because you would get silver chloride coming out of solution. 50. How would you prepare the following substances by a precipitation reaction? I mean, that's kind of weird, but you could mix lead 2 nitrate plus sulfuric acid would be a way to make lead sulfate. Magnesium phosphate, you could do magnesium chloride plus phosphoric acid. Zinc chromate, you could do potassium chromate plus zinc chloride, I guess. That's weird. What the heck do they mean by that, I wonder? 268. So let's see, we're A30, wasn't it? Yes, it was. So, lead nitrate plus sodium sulfate. Yep, magnesium chloride, potassium phosphate. Yeah, and zinc sulfate plus sodium chromate. Yeah, there's plenty of options for that. That was a weird problem. Just they asking you to come up with soluble. Okay. 52. What is the mass and identity of the precipitate that forms when 30 mils of 0.15 molar hydrochloric acid reacts with 25 mils of 0.2 molar silver nitrate? Well, you're going to get silver chloride. And as for the mass, well, they're asking you to do quite a bit of math there. Let's see, hydrochloric acid, silver chloride, so it's all going to be 1-to-1. So let's see. 0.0300 liters times 0.150 molar HCl means I'm going to need my calculator for this. I should have opened that up before. It's going to be 0.0045. 0.03 times 0.15. Okay, 0.0045. So that is the HCl. And as for the silver nitrate, it was 0.25, 25 mils of 0.2 molar. Okay. I'm finding the limiting reagent now, limiting reactant. 0.025 times 0.2, it's going to be 0.005. Yeah. Okay, so this is your limiting reagent because there's less of it. The silver nitrate plus HCl is just a 1-to-1 to 1-to-1, so no need. Well, I mean, you technically divide by 1, and that tells you. All right, so you're going to make 0.0045 moles of silver chloride. Now we need the molar mass of silver chloride. This one I did open up beforehand. That's the periodic table. Silver is 107.87. Chlorine is 35.45. 107.87 plus 35.45. 143.32 grams per mole. So times 0.0045. Well, technically, it's 3 sig figs. So equals 0.645 grams of silver chloride. Okay. So perfectly standard Stoic problem. And that was problem 52. Do we have to go further than that? Yes, we're going to 56. Okay. Yep. 54. Assume that you have an aqueous mixture of sodium nitrate and silver nitrate. How could you use a precipitation reaction to separate the two metal ions? Add some hydrochloric acid, you'll get silver chloride out. Huh. Well, if you want to work with something slightly safer, you could do table salt. But yeah, sodium chloride, yeah, would also do the trick. Assume that you have an aqueous solution of an unknown salt. Treatment of the solution with dilute sodium hydroxide, sodium sulfate, and potassium chloride produces no precipitate. Which of the following cations might the solution contain? It's not going to be silver, because the silver would have come out with the hydroxide and the chloride. Might it be cesium? No, cesium. Well, yeah, cesium it could be, because that one is always soluble. Barium would also produce... No, barium would produce a thing with sulfate, so not barium. NH4 would also not produce any thing. So it could be either cesium or ammonium, but not silver or barium. Silver would form a precipitate with the potassium chloride. Barium would produce a precipitate with the sodium sulfate. All right, problem 60. Are the balanced ionic equations for the following reactions. Aqueous perchloric acid is neutralized by aqueous calcium hydroxide. So, that's easy enough. Boop, boop, boodly-doo. Perchloric acid and calcium hydroxide. Oh, they wanted ionic equations, not molecular equations. So 2H plus 2ClO4 minus plus calcium 2 plus 2OH minus yields calcium 2 plus 2ClO4 minus plus 2H2O liquid. Next up, sodium hydroxide neutralized by acetic acid. Okay, so that's just 1-to-1. Forgive me for not putting the things on there. That takes more time and it's boring. All right, so 60 was fairly straightforward. Who's next? 62, 64, 70, 72, 74, 76, 77. Okay, so we're going straight through to 78. From where? From where we are. From 60 straight through to 78. Okay. All right, balanced net ionic equations, lithium hydroxide plus hydroiodic acid. Well, that's just going to be H plus OH minus goes to H2O. And so is the next one. I mean, that's not even hard. They're just acid-base neutralizations. I mean, am I missing something? No, I'm not. That's literally all they want. That's kind of goofy. Okay, 64. The following solutions are mixed. Is the resulting solution acidic, basic, or neutral? Okay, this is a limiting reactant problem. They're just asking, are you going to have acid left over or base left over? 50 mils of 0.1 molar versus 30 mils of 0.2 molar, that's going to be basic. You're going to have 0.05 moles of the hydrobromic acid and 0.005 moles of the hydrobromic acid and 0.006 moles of the potassium hydroxide. So you're going to have a little potassium hydroxide left over. The hydrobromic acid's the limiting reactant. 100 mils of 0.075 or 75 mils of 0.1. That's going to be neutral. Good thing I caught that. It's barium hydroxide, so that's a 2-to-1. So it's going to be basic when all is said and done. 0.1 times that is going to be 0.0075. 0.1 times 0.075 there is also going to be 0.0075. So yeah, you're going to have 2 hydroxide ions for every 1 H plus ion. 66. How many milliliters of 1 molar potassium hydroxide must be added to neutralize the following solutions? a mixture of lithium hydroxide and hydrobromic acid. Interesting. They used weird numbers. I'm going to actually have to write it down. Okay. That's inconsiderate of them. 25 mils of 0.24 molar is 0.240 molar times 0.0250 liters. 0.24 times 0.025. No. 025. 025. 0.006 moles of our lithium hydroxide. And how much hydrobromic acid are we looking at there? 0.2 molar times 0.075 liters. That's going to be 0.2 times 0.075, 0.015 moles of the HBr. That's a 1-to-1 ratio, so it's just going to be minus 0.006, 0.009 moles of HBr left over. And we need potassium hydroxide. We have 1 molar potassium hydroxide. So that's 1 mole per liter. So we need 0.009 liters equals 9 milliliters of our KOH in order to neutralize that. You guys should be more careful with the math. I'm rushing through this because I got Assassin's Creed Valhalla and I want to go play it. All right, a mixture of 0.3 molar HCl and 0.25 molar sodium hydroxide. Okay, it's still going to be acidic, but 0.3 times 0.045 is equal to 0.0. 135 moles HCl. And from that, we're going to subtract how much sodium hydroxide? 0.0025 moles NaOH. Double checking, 0.01, nope. 0.01 times 0.025. Did I do 0.01? Yes, I did. And I should have, because it's 10 mils. All right, so it's 0.00025. So it's 0.01325 moles HCl. So we need 13.25 mils of the KOH. 68. Where in the periodic table are the best reducing agents found? The best oxidizing agents. Best reducing agents are over here, the top left-hand corner. Or actually, let's see. Yep, top left-hand corner is the best reducing agents. Best oxidizing agents are the top right-hand corner. Where in the 70. In each of the following instances, tell whether the substance gains electrons or loses electrons in a redox reaction. An oxidizing agent is reduced, so it's gaining electrons. A reducing agent is oxidized. No, wait. An oxidizing agent is reduced, it's gaining electrons. Okay. A reducing agent is oxidized, it's losing electrons. Undergoing oxidation means losing electrons. Undergoing reduction means gaining electrons. Assign oxidation numbers to each element in the following compounds. Okay, I'm going to power through this one. Oxygen is negative. Okay, so A is NO2. Oxygen is -2. Nitrogen is +4. B, SO3. Oxygen is -2. Sulfur is +6. C, COCl2. Let's see, oxygen is -2. Chlorine is -1. So carbon is +4. CH2Cl2. Hydrogen is going to be +1, chlorine is going to be -1, so carbon is going to be 0. Potassium chlorate, potassium is +1, oxygen is -2. ClO3, 1 minus, chlorine is going to be +5. Likewise, nitrogen here is +5, because it looks exactly the same. H plus, 1 plus, 2 minus on the oxygen, and then nitrogen is +5. More oxidation numbers, powering through ClO3 1 minus. We literally just did that one. Chlorine is positive 5, oxygen is negative 2. SO3 2 minus. Sulfur is going to be positive 4 in that one. Let's see, wait, oxygen is going to be total negative 6. Something minus 6 is negative 2. Yes, sulfur is positive 4. C2O4 2 minus. Oxalate. Oxygen is still negative 2. So 2 carbons minus 8 is negative 2. 2 carbons is positive 6. Each carbon is positive 3. Nitrite. Oxygen is negative 2, so nitrogen is going to be positive 3. Hypobromite. Bromine is going to be positive 1. Oxygen is negative 2. Arsenate. O4 3 minus. Okay, so oxygen is negative 2. Arsenic is going to be positive 5. 76. Which element is oxidized and which is reduced? Calcium is going to calcium 2 plus, so it's being oxidized. Tin is going from 2 plus to 0, so it's being reduced. ICl plus H2O goes to HCl plus HOI. Weird. Okay, so I'm going to go ahead and assume that iodine and chlorine are going to be 0 each in the ICl, iodine chloride, iodine monochloride. And therefore, chlorine is being reduced to 1 minus, and iodine is being oxidized to 1 plus. Interesting. I'm going to check that one. For 76. It's not a redox reaction. Okay. I was overthinking it. I missed the obvious. Okay. 78. Use the activity series of metals to predict the outcome of each of the following reactions. Will zinc reduce sodium? It will not. So we go back to page 255 to double check that. Is zinc above sodium? It's not going to be above sodium. It's zinc is down here, sodium is up here, so no. Zinc will not reduce sodium. No, you're not going to get a reaction between hydrochloric acid and platinum. Like I said, the noble metals don't react with acid, and platinum is one of the noble metals. Silver and gold. No, silver is not going to oxidize gold. Will gold oxidize silver? It absolutely will. Yes, the only one of these reactions that will occur is D. I think we go through to 80 something. So, nope, we're going to skip ahead to 82 now. Oxidation or reduction half reaction. So nitrogen is going from positive 5 to positive 2. It's going down, so that's a reduction. That's a reduction half reaction. B, zinc is being oxidized. That's an oxidation half reaction. Titanium is going from positive 3 to positive 4. That's an oxidation half reaction. Tin is going from plus 4 to plus 2. That's a reduction half reaction. Now we'll skip ahead to 86, and we're going to go to 92, then 96. Right, unbalanced oxidation reduction half reactions for the following. Okay, so we're just breaking these. Oh, come on. Come on, that is the easiest thing in the world. I mean, identifying them as oxidation or reduction is slightly harder, but the tellurium is going from 0 to 4 plus. That's your reduction, or sorry, your oxidation half reaction. The nitrogen is going from plus 5 to plus 2. That's your reduction half reaction. I mean, it's just TE to TeO2. Boom, that's one. Nitrate to nitric oxide. That's the other one. H2O2 goes to H2O. That's your reduction half reaction. Fe2 plus to Fe3 plus is your oxidation half reaction. All right, 86. Ooh, balance the following half reactions. Okay. Oh, this is where my do it all in one swell foop thing is kind of ruining me. Let's see. Okay. No. No, because, I mean, balancing a half reaction all by itself in an acid is not a problem for me. I never learned a method for balancing the half reactions as if they were in a base all by themselves. So, let's see. No, you couldn't balance... Could you balance the oxygen by adding hydroxide instead of water? Maybe. But then you would have to... No, I have... Okay, let's try this. I'm going to... Okay, so, well, I'll go ahead and do the first one. Balance that half reaction. I can do that easily enough. Then I'll try to wing it on the other three, because they're all basic. Alright, so Cr2O7 minus goes to Cr3 plus. We're going to need 2 of our Cr3 plus. We're going to need 7 water, which means we need 14 H plus. So that means we need 6 electrons. Okay, that one worked out super easy. But now CrO4 minus goes to CrOH4, OH4 1 minus. Okay, so let's try balance oxygen. Okay, chromium is balanced, oxygen is balanced, so 4H plus. Now we're going to do plus 4OH minus plus 4OH minus. So this makes 4H2O and 4OH minus there. Okay, so that looks hard to read. So now, hopefully, everything's still balanced. 4 plus 4 makes 8 oxygen. 4 plus 4 is 8 oxygen. 4 times 2 is 8 hydrogen. 4 plus 4 is 8 hydrogen. Now we just need to balance the charges. We have 1 minus and 5 minus, so we need 4 electrons. Okay, yeah, so that's balanced. Okay, so what did that amount to? We would have added 4H plus to this side. Instead, we added 4 water and 4 hydroxide. That's what it amounted to. Okay, so let's give that a shot. Let's see if that continues to work out for us. Bismuth 3 plus goes to BiO3 1 minus. So we'll have 3 water. Now we would add 6 hydrogens over here. Instead, we're going to have 3 H2O. Those 3 H2O go away. We'll end up with 3 OH minus over here. 0 and -1, we need 1 electron. That seems wrong. Three plus is going to 5 plus, so there should be 2 electrons over here. Oh, because this is 6 OH minus. Okay. Okay, that's where I screwed myself up. Because I added 6 waters to this side, 6 minus 3 gave me 3. So there's 6 hydroxides. Okay, or I added 6 H plus, which meant 6 water. Okay, so that means we have 3 minus and 1 minus. Yes, good. We need 2 electrons over here. Okay, okay, all right. I'm kind of getting it. ClO minus goes to Cl minus. Water. So we have 2 water. No, wait. So 1 water over here. So that would be 2 H plus over here. So instead, we're going to get 2 water minus the 1 water, so H2O plus 2 OH minus. So this is going to be 2 electrons, yes? This is going from 1 plus to 1 minus. Yes, good. And let's see, 2 oxygens, 2 oxygens, 2 hydrogens, 2 hydrogens. Okay, all right. Okay, I'm kind of getting the hang of this. This is kind of weird. I'm having to think my way sideways through these things. All right. That was 88. 90. Write the balanced net ionic equations for the following reactions in basic solution. Okay, so just we're balancing these redox reactions. All right. That's balanced net ionic. That's weird. Okay. MnO4 minus, IO3 1 minus. Okay, so MnO4 minus is turning to MnO2. So we need 2 waters. So, no, 2 waters. So we need 4H plus, which means we need 3 electrons. So 7 plus down to 4 plus. Yes, good. Now, what was the other half? IO3 to IO4. IO3 1 minus goes to IO4 1 minus. We need 1 water. We need 2H plus and 2E minus. Wait, IO3, yeah, okay, good. So now to balance them against each other, we're going to need 2, 8, 6, 2, 4 versus 3, 3, 3, 6. Our electrons disappear entirely. Most of the water disappears. All but 2 of the H plus. So 2 MnO4 minus plus 3IO3 minus plus 2H plus goes to 2 MnO2 plus 3IO4 minus plus H2O plus 2OH minus plus 2OH minus 2H2O. That goes away. That goes down to 1. 2 MnO4 minus plus 3IO3 minus plus H2O yields 2 MnO2 plus 3IO4 minus plus 2OH minus. Ran out of room. So 2 manganese, 2 manganese, 3 iodine, 3 iodine. 8 plus 3, or sorry, 8 plus 9 makes 17 plus 1 makes 18 oxygen. 4 plus 12 is 16 plus 2 makes 18 oxygen. 2 hydrogen, 2 hydrogen. Total charge is -2, -3, for a total of -5. -3, -2 for a total of -5. Okay, everything works. That is balanced. All right, copper 2 hydroxide plus N2H4. That's rocket fuel. I think it's azide is what it's called. No, azide is N3. Whatever. All right, so CuOH2 goes to form just copper. So 2H2O, 2H plus, 2E minus. Yeah, all right, and the other half into H4 goes to N2. Into H4, N2 plus 4H plus 4E minus, so we double everything up here. The electrons and the hydrogen both completely disappear, and we're just left with 2CuOH2 plus N2H4 yields 2Cu plus N2 plus 4H2O. Yeah, that makes sense. All right, next up, iron 2 hydroxide, FeOH2 plus, well, going to iron 3 hydroxide. So we're going to need 1 water, which means we need 2H plus. No, that can't be right. 2 oxygens. Did I? Okay, so 2 oxygens versus 3 oxygens. We need the 1 water. Oh, no, we only need 1 H plus. Good. Okay. Well, the reason I was thinking it was wrong, because to balance the charge, it would have had to have been 2 electrons, but I knew it was only 1 electron because 2 plus to 3 plus. So, all right. Now the other half is CrO4 2 minus, turning into CrOH4 1 minus. CrOH4 1 minus. Chromium is balanced, oxygen is balanced. We need 4H plus, which means we need, let's see, 2 plus versus 1 minus. We need 3 electrons. So we need to multiply this guy by 3. Our electrons cancel out. Most of our hydrogens cancel out. None of the water. Okay. So 3FeOH2 plus CrO4 2 minus plus 3H2O plus H plus yields 3FeOH3 plus CrOH4 1 minus. We add OH minus, OH minus. That's going to give us 3FeOH2 plus CrO4 2 minus plus 4H2O yields 3FeOH3 plus CrOH4 1 minus plus OH minus. Okay, so 3 iron, 1 chromium, 1 chromium. 3 times 2 is 6, plus 4 is 10, plus 4 is 14 oxygen. 3 times 3 is 9, plus 4 makes 13, plus 1 is 14 oxygen. Was that what I said? 6 plus 4 is 10, plus 4, yes, is 14, okay. 6 hydrogen plus 8 is 14 hydrogen. 3 times 3 is 9, plus 4 is 13, plus 1 makes 14 hydrogen. Okay, that's all the elements. Charge, -2, -1, -1. Okay, so everything balances out. Okay. Going to change color. This green is starting to make me sad. Last one, hydrogen peroxide plus perchlorate. So H2O2 goes to O2 plus 2H plus 2E minus. And on the other hand, perchlorate goes to chlorite. ClO4 2 minus makes ClO2 1 minus plus 2H2O plus 4H plus. No, it's ClO4 1 minus. What am I thinking? Plus 3 electrons. Yep, so we're going to triple up top. 3, 3, 6, 6. Double down here, so 2, 8, 6, 2, 4. The water doesn't do anything. The electrons disappear. 8 minus 6 leaves us with 2H plus. Okay. What are you doing, open? Go away, you stupid thing. So plus 2OH minus plus 2OH minus 2H2O, so that goes away. This goes down to 2. 3 hydrogen peroxide plus 2 ClO4 minus plus, nope, not plus, just goes to 3O2 plus 2 ClO2 1 minus plus 2 H2O plus 2 OH minus. 6 hydrogen versus 4 plus 2 is 6 hydrogen. 3 times 2 is 6 oxygen, plus 8 is 14 oxygen. 6 plus 4 is 10, plus 2 makes 14. 2 chlorine, 2 chlorine. Charge over here is -2. Oh no. What went wrong? Chlorine went from 7 plus down to 4 plus, 3 plus. Yeah, so it should have been 4 electrons. Yep. Yep. I screwed up way up there. It's not 3, that's 4. Okay, let's redo this. I mean, I got the hydrogen peroxide one correct, so I can keep that one. H2O2 goes to O2 plus 2H plus 2E minus. We're going to end up multiplying this guy by 2. I'll tell you that for free. So on the bottom, ClO4 minus, ClO2 minus plus 2H2O plus 4H plus 4E minus. I done screwed it up. Okay, so, yep. Now, the electrons disappear, and so do the H plus. Oh, that's nice. So 2H2O2 plus ClO4 minus yields 2O2 plus ClO2 minus plus 2H2O. So now, even less work. Okay, so 4 hydrogen plus 4 hydrogen. 4 plus 4 is 8 oxygen. 4 plus 2 is 8 oxygen. Charge is -1 and -1. Oh, and 1 chlorine, 1 chlorine. Okay, so everything balances out now. See? It's easy to make mistakes in these things. Okay. So that was 90. 92. Oh, more. I'm not going to do those. I'm just executive decision. I'm skipping that. Dichromate reacts with aqueous iron 2 to produce the following balanced equation. So the dichromate is the oxidizing agent. The iron is the reducing agent. Okay. What is the concentration of Fe2 plus if 46.99 mils, 0.2004 molar potassium dichromate is needed to titrate 50 mils of the Fe2 plus? Okay, this looks more difficult than it is. This is just a titration reaction. So it's just basic stoic. All right. Okay, so 0.04699 liters times 0.2004 moles per liter. Bring up the calculator. 0.04699 times 0.2004. 0.0046 figs, so 9417 moles of our dichromate. 2072 minus. And then they give us the ratio. It's 1 to 6. So times 6 moles of Fe2 plus per every 1 mole of the dichromate. So times 6 equals 0.05650 moles of Fe2 plus. And then it was in 50 mils, so we divide by 0.0500. Oops. 0 liters. Is 1.130 molar. Okay, so that was 92, 96. Oh, that's it. We're done with Chapter 7. Oh, I don't really want to do Chapter 8. That's a lot of problems. But then tomorrow I won't want to do Chapter 9 if I do Chapter 8. Okay. So I'm just going to go ahead and do the first line. I'm going to do through problem. I'll see how far I get before I get bored and tired. Okay, so we're starting with problem 28 there in Chapter 8. So we need to go back a few pages. Not far enough. All right. Oh, this is going to be a lot of math. This is going to go a lot slower than Chapter 7. All right, well, imagine a reaction that results in a change in both volume and temperature. Has any work been done? If so, is it positive or negative? Yes, work has been done, and the sign is negative. The system has expanded, so it's done work. Is there an enthalpy change? Yes, heat has gone into the system, and it is a positive sign, so it is going to be endothermic. Oops. Now 32 to 36. Oops. Reaction is carried out in a cylinder fitted with a movable piston. The starting volume is V equals 5 liters, and the apparatus is held at constant temperature and pressure. Assuming that delta H is negative 35 and delta E is negative 34.8, redraw the piston to show its position after the reaction. Let's see. Delta E equals Q minus P delta V. We know this and this. Negative 34.8 equals negative 35. 0 minus negative 0.2. Okay. So P delta V is negative 0.2. It's against 1 atmosphere of pressure, so delta V is negative 0.2. So, yeah. So that means it is going to expand by 0.2 liters. So it's going to be 5.2 liters. Let me double check. When it began. No, it decreases from 5 to 3. Okay, so let me go through, and I should have remembered the page number. So 314. Yeah, oh, no. 312. 09. Yes, okay, so delta E is negative 34.8. Delta H is, okay. Okay, so P delta V is negative 0.2. Delta V equals constant temperature and pressure, so it's still at 1 atmosphere. I'm confusing myself somehow. Delta E is equal to negative 34.8. It's also equal to Q plus W. We know Q, so W equals negative 34.8 minus negative 35. So unless I am greatly mistaken, (34.8) negative minus 35 negative. So W equals 0.2. So negative P delta V equals 0.2. P delta V equals negative 0.2. Delta V equals negative 0.2 divided by P. P is just 1 atmosphere equals negative 0.2. Oh, okay. Okay, among other things, I forgot to change it from atmospheres, so it's still divided by P, to 101,325 pascals. Okay. Oh, and also this is kilojoules, so this is negative 200 joules divided by that many pascals is going to be 200 divided by 101,325 is 0.001974 cubic meters times 1,000, that's 1.974 liters. Okay, so it's decreasing by about 2 liters. Okay, that's what I was doing. I was forgetting. I forgot. I should have been more careful. I was not paying attention to my units. Okay. Be humble, be humble. Be you ever so humble. Okay, 34. What are the signs of delta H, delta S, delta G for this following spontaneous change? It looks like it's getting colder because it's getting blue. But I mean, it looks like it's going from a liquid to a gas. So delta S is definitely positive regardless. It's spontaneous, so delta G is negative. So delta H could be positive or negative for this, but I mean, it's turning blue. So it looks like it's getting, so the surroundings are getting colder. Maybe that's what it means. So it's an endothermic. So it could be an endothermic reaction for that, but they're not really giving any indication for what they mean. I have no way of really judging the delta H there, unless that blue is supposed to indicate something. Delta G is less than 0, delta H is greater than 0, and delta S is greater than 0. Okay. If the surroundings are getting colder, that's what I guess that blue means. Then it would be an endothermic reaction, so delta H would be positive. Okay, 40, 44. Oh, well, let's just do 40, and then we have a whole bunch in a row. So 40. Next page. Calculate the work done in joules by a chemical reaction if the volume increases from 3.2 liters to 3.4 liters against a constant external pressure of 3.6 atmospheres. All right, so negative P delta V, it's expanding, so it's going to be doing work. It's going to be negative, so that's the sign of the change. So it's going to be 3.6 times 0.2 is 0.72 times 1 liter atmospheres times 101.325 joules per liter atmosphere. .6 times 0.2, just double checking, good, times 101.325 is 72, let's call it 73 kilojoules. And it's negative because it's expanding. The system is doing work on the surroundings. I always double check myself on these, and obviously not on top. Negative 70. Okay, they are weird. Okay, maybe they're using a slightly different version of joules per liter atmosphere. Whatever. So now we're going to be doing problems 44, 54, 56, 58. So 44 through 58. 58 is where we're going to be stopping. A reaction inside a cylindrical container with a movable... Oh, you couldn't see any of the work I was doing. I didn't have this stupid thing on. Okay. So the previous problem where I was having trouble, you can see the math. This is where I forgot to do first convert to pascals, and then I had to convert back to liters. Okay. And then there's that. Okay, whatever. A reaction inside a cylindrical container with a movable piston causes the volume to change from 12 to 18, while the pressure outside remain constant at 0.975 atmospheres. What is the value in joules of the work done during the reaction? Okay, so delta V is positive 6, and P is 0.975, so that means P delta V is 6 times 0.975, 6 times 0.975. Yep, that's going to be, that's the liter atmosphere, so we multiply by 101.325. No, got to divide by 1,000. It's 101.325. Means it is 593 joules of work, and it is negative because it's an expansion. And now, what is the diameter of the piston is 17 centimeters. How far does the piston move? Pi r squared h. Okay, so from 12 to 18. So so 17 centimeters is 1.70 decimeters. I'm changing it to decimeters because a liter is in cubic decimeters. So I'm saving myself some trouble later on. So volume equals pi r squared h. This is the diameter, so I'm going to need to cut it in half. Dang it. So our volume, pi r squared h. So volume is equal to pi times half of that is 0.850 decimeters squared times h. And the total volume was 6 liters, 6.0. So the height, so this is cubic decimeters, yes. So the height is equal to 6.0 cubic decimeters divided by pi, which is, and divided by 0.850 decimeters, quantity squared. So 6 divided by 3.14159 divided by 0.85. It moved a total of 26.4 centimeters, unless my brain done farted again. So we're in 44, negative 593, nailed that one. And 26.4 centimeters, nailed that one as well. I am very good at solving problems. Okay, back to page 310. Okay. 46. What is the difference between heat capacity and specific heat? All right. Heat capacity is the amount of energy needed to change the temperature of an object. The specific heat is the amount of energy needed to change the temperature of 1 gram of a substance. Okay, so specific means per gram. That's what specific means in this context. Heat capacity is for some object. Specific heat is for a substance. So water, regardless of how much you have, all has the same specific heat. But a liter of water has a different heat capacity from 10 liters of water. 48. Sodium metal is sometimes used as a cooling agent in heat exchange units because of its relatively high molar heat capacity of 28.2 joules per moles degree Celsius. What is the specific heat of sodium in joules per gram degree Celsius? Okay, well, this is just a molar mass thing. So bring up the paper and bring up the calculator. So we have 28.2 joules per mole degree Celsius. We need to get rid of moles and replace it with grams, so we're dividing by the molar mass of sodium. So 28.2 divided by 22.99 is 1.23, oopsie, you can't read anything I'm writing, joules per gram degree Celsius. And that is relatively high. All right. Still nothing compared to water, but still relatively high. 50. 1.045 grams of calcium oxide is added to 50 milliliters of water at 25 degrees Celsius in a calorimeter. The temperature of the water increases to 32.3 degrees Celsius. Assuming that the specific heat of the solution is 4.18 and that the calorimeter itself absorbs a negligible amount of heat, calculate delta H in kilojoules for this reaction. Just kilojoules. Okay, so Boom, 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 boom. So the temperature is changing by +7. Okay. So Q equals mc delta T equals okay, so I'm going to also assume, even though they don't tell us, that 50 mils of water is 50 grams of water. So that would be 51.045 grams for our solution, 4.18 joules per gram degrees Celsius, and then a temperature change of 7.3 degrees Celsius. All right. 51.045 times 4.18 times 7.3 is 1558 joules. That's the amount of heat going into the water, so the heat leaving the reaction is negative 1558 joules. And then the calcium oxide is going to be our limiting reagent, so we'll need the molar mass of calcium oxide. Calcium is 40.078. Okay, oops. So 40.078 plus 15.999, 56.077 grams per mole. 1.045 divided by 56.077 is 0.01864 moles of calcium oxide. So delta H is equal to negative 1558 joules divided by 0.01864 moles. Delta H is Q over moles. So 1558 divided by 0.01864 is negative 83.6 kilojoules per mole. So let's see which of all those numbers they were looking for, because this question was unclear. Just a little bit. Just a little bit unclear. Okay, so yep, 83.6. That's what they were looking for. Okay. So all of the assumptions that I had to, just sort of cram in there that they didn't tell us to do were right. We were looking at 50 mils is equal to 50 grams of water. So the total mass of our solution was 51.045, the calcium oxide and the water together, which is how I got this heat of 1,558 joules. So that's the amount of heat entering the solution, so it had to come out of the reaction. And then our calcium oxide was our limiting reactant, so that determined the moles we divided by. So 0.01864, so Q divided by N gave us the heat of our reaction, delta H. Okay, so what problem was that? That was 50. And I have been talking into Mike for more than an hour, but I'm going to keep on going. I'm going to soldier on. 52, 54, 56, 58. Okay, we keep on going till 58. Okay, when a solution containing 8 grams of sodium hydroxide and 50 grams of water is at 25 degrees Celsius is added to a solution of 8 grams of HCl and 250 grams of water at 25 degrees Celsius in a calorimeter, the temperature of the solution increases to 33.5 degrees. Assuming that the specific heat of the solution is 4.18 and that the calorimeter absorbs a negligible amount of heat, calculate delta H. Okay, so 8 grams of sodium hydroxide versus 8 grams of HCl. One of those is going to be our limiting reactant. Okay. Okay, we'll find the we'll answer the second question later. First up, our total mass is 316 grams. Q equals mc delta T. Our total mass. Our total mass is 316.0 grams. That's the mass of the two waters and the sodium hydroxide and the HCl, and it's 4.18 joules per gram degrees Celsius. And then our delta T is 8.5 degrees. $316 times 4.18 times 8.5. So we're looking at 11,200 joules going into the water. That's Q of the reaction is equal and opposite is negative 11,200 joules. Okay, so now we need to find our limiting reactant. 8 grams of sodium hydroxide versus 8 grams of the sodium hydroxide is going to be the limiting reactant. Because sodium hydroxide has a molar mass of 23 plus 16 plus 1, it's about 40. HCl, it is H plus and Cl minus is about 36.5. So that means that it has, yeah, I'm shortcutting some of the math. The sodium hydroxide is our limiting reactant. So 22.99 plus 15.999 plus 1.008, 39.997. Okay, so 8 divided by 39.997. So delta H equals negative 11,200 divided by 0.2000. So that's going to be, we're multiplying by 5. 55 plus 1 equals negative 56.0 kilojoules per mole. Okay. 52. When the experiment is repeated using a solution of 10 grams of HCl and 248 grams of water, the same temperature increase is observed. Explain. Okay, so you'll notice that they changed the mass of hydrochloric acid, of hydrogen chloride. They moved that up by 2, but they kept the total mass of the solution the same by decreasing the amount of water by the same amount. So that's why you're able to get this same thing. But the reason the temperature change is the same is because the sodium hydroxide was a limiting reagent or limiting reactant. If the HCl had been a limiting reactant, then you would have seen a change in temperature. Okay, what is the difference between the internal energy change, delta E, and the enthalpy change, delta H? Technically, the difference is work, P delta V, because delta H is equal to delta E plus P delta V. Which of the two is measured at constant pressure and which at constant volume? Delta H is measured at constant pressure, delta E is measured at constant volume. 56. Under what circumstances are delta E and delta H essentially equal? Low pressure. A low pressure or a small change in volume would be essentially equal. And atmospheric pressure, 1 atmospheric pressure is pretty low pressure. But I want to double check that. I want to make sure that they are thinking the same thing I am there. Nope, not quite. So 56, nearly equal, when there are no gases involved in the chemical reaction, or if the gases involved, or if gases are involved, the delta V is equal to 0. Okay, so essentially, they're equal when there's no work. All right, finally, number 58. Well, not finally, but next up, number 58. The enthalpy change for reaction is what is the value of E? Enthalpy change for the reaction of 50 mils of ethylene with 50 mils of hydrogen is, that's the same as problem 41. Okay, so I'm assuming that, yeah, that's what I thought. Okay, so we're adding 50 mils of ethylene with 50 mils of H2 at 1.5 atmospheres of pressure. Delta H is negative 0.31 kilojoules. What is the value of delta E? All right, so you're combining two gases, and you're going to end up with one gas. So essentially, the volume is going to go down. You have 50 mils of ethylene and 50 mils of hydrogen. You react them together. The final volume is going to be 50 mils. So your volume is getting cut in half. So delta V is going... Oops. Gotta remember to turn this on. So delta V is going to be 0.0500 liters minus 0.100 liters, essentially. Yeah, that's... I would not have asked this question in this chapter because it's kind of weird. All right. And delta H is 0.31. So that means that P delta V is going to be 1.5 atmospheres times negative 0.05 liters. It's going to be 0.075 liter atmospheres, I think. 0.05 times 1.5. Yes. Oh, wow. I am very good. Okay, so then we multiply that by 101.325. Oh, negative. Times 101.325. P delta V is negative 7,600. So delta H equals negative 0.31 kilojoules. Yeah, so negative 310 joules. Delta E is, so that's equal to delta E plus P delta V. So delta E equals negative 310 minus negative 7,600 equals positive 7,290. No, that's wrong. Okay, what did I do wrong there? Oh, okay. Okay. Okay, let's try this again. Okay, so I got the final volume right. It is 50 mils. Ba-ba-da-ba-doo, bow-bow, ba-da-da-bow-ba-down. Ba-da-da-bow-ba-down. All right. Delta E equals delta H minus P delta V equals negative 0.31 kilojoules minus 1.5 atmospheres times 0.05 liters times 101.325 joules per liter atmosphere. So 1.5 times 0.05 times 101.325. Obviously, oh, how did I end up oh, because I did 101.325. Okay. Okay. I slipped a decimal place. Okay, that will definitely that will definitely do it. So divide by 1,000 to get it into kilojoules. Yeah. So it's going to be a negligible difference. Okay. Because 0.31 minus 0.007. Yeah, that'll round to 0.30. Okay. Yeah, okay. So obviously I'm getting too tired. I should not continue with this. I'm going to stop at problem 58. I'll continue from problem 62 starting tomorrow evening. And then I'll do a little bit more work on chapter 9. I'll see you guys around.